In this lesson, we'll look at applying the concept of circular motion. So from the introduction lesson, we should know that omega is our angular velocity. What it is the rate of change of the angle with respect to time. We should know that the magnitude of the velocity or the speed is equal to the angular velocity multiplied by the radius. We should know that the dot product of the direction and the velocity is equal to 0, which means that the direction of motion is perpendicular to the position vector, which really means that the radius at any point in time, the velocity or the direction of motion will be perpendicular. Okay. From that, the other thing that we need to know is that the position vector with respect to time is going to be r cos omega t in the I direction and r sine omega t in the j direction. It should also be noted that because we're looking at uniform circular motion, which is periodic motion, omega will be 2 pi on the period, where the period is time to complete one cycle. Okay, so we'll look at a couple of examples now. In this first example, we're looking at a scenario where we've got a particle moving around a circle of radius 3 meters, constant speed of 2 meters per second, and we're given that at time 0, the angle is equal to 0. So it means we can use our uniform circular motion equations. Okay, so we know that r is equal to 3. We know that the velocity is 2 meters per second. And we know what we do need is our angular velocity to be able to start. So part A is actually asking us what's our angular velocity. Now we know that v is equal to omega r. So we know that 2 is equal to omega multiplied by 3. So omega will be 2/3. Now the units for this will be radians per second. Okay, so then when we look at part B, we're looking at the position of the particle at time t equals pi seconds. So first of all, we need that position function. So position will be r cos omega t, the I direction, and r sine omega t in the j direction. So we get 3 cos 2/3 t in the I direction and 3 sine 2/3 t in the j direction. So when t is equal to pi, so we get r pi is equal to 3 cos 2 pi on 3 in the I direction and 3 sine 2 pi on 3 in the j direction. Now 2/3 pi leaves us with pi on 3 to the nearest axis, and using cast, only sine will be positive in this section. So we can say this is negative 3 cos pi on 3 in the I direction, and this is 3 sine pi on 3 in the j direction. Cos pi on 3 is 1/2, so we get negative 3 multiplied by 1/2 in the I direction. And sine pi on 3 is root 3 on 2, so we get 3 root 3 on 2 in the j direction. And we're left with negative 3 on 2i and 3 root 3 on 2 in the j direction. So a good example why you need to be fluent with your standard triangles. Part C asks for the velocity of the particle at time t equals pi. So the velocity vector is going to be derivative of the position vector. Means we will have negative 2/3 multiplied by 3 sine 2/3 t in the I direction, and 2/3 multiplied by 3 cos 2/3 t in the j direction. So we get -2 sine 2/3 t in the I direction and 2 cos 2/3 t in the j direction. When t is equal to pi, we can look at -2 sine 2 pi on 3 in the I and 2 cos 2 pi on 3 in the j direction, which is -2 multiplied by root 3 on 2 and 2 multiplied by -1/2. So left with -√3 in the I direction and -1 in the j direction. So our velocity vector at that point in time is -√3i subtract j. The final question is looking at acceleration. With acceleration, we're saying the acceleration vector is r dot dot, so the second derivative. So we're taking the derivative of the velocity vector, and we can say that is -2/3 multiplied by 2 cos 2/3 t in the I direction, and -2/3 multiplied by 2 sine 2/3 t in the j direction. So we end up with -4/3 cos 2/3 t in the I and -4/3 sine 2/3 t in the j direction. Now, when t is equal to pi, we've got -4/3 multiplied by -√3 on 2, -1/2 in the I direction, and we have -4/3 multiplied by √3 on 2 in the j direction. So we're left with 2/3 I and -2√3 on 3 in the j direction. And that is in meters per second squared. Obviously the velocity will be meters per second. And the position vector, meters. Now all of this highlights how important it is to be fluent with your vector calculus, but also your trigonometry from Unit 2. So to look at a final example, what we've got is a particle moving at a constant speed of 8 meters per second around a circle at a radius of 4 meters. So we're assuming the same things, which means we can treat it as uniform circular motion. So we should be able to say that v is equal to 8, radius is equal to 4, and from that we can say that v is equal to omega r. So we have 8 is equal to omega multiplied by 4, and omega will be 2. So that angular velocity will be 2 radians per second. Now we're being asked to find for part A the position of the particle relative to the center of the circle. So we can say again that RT is R cos omega t in the I and R sine omega t in the j direction, which gives us 4 cos 2t in the I and 4 sine 2t in the j. This is our function with respect to time. Part B, find the velocity of the particle at time t seconds. So the velocity function will be the derivative, which means we're going derivative of 4 cos 2t, which will be -8 sine 2t in the I direction, and derivative of 4 sine 2t, which will be 8 cos 2t in the j direction. And so that function is in meters per second. Finally, to find the acceleration of the particle, it's a double derivative of the position vectors. So that's the derivative of the velocity vector. The derivative of 8 sine 2t will be 16 cos 2t in the I, and derivative of 8 cos 2t will be negative 16 sine 2t in the j, and that's in meters per second squared. Okay, so it's as simple as that. If we had to say part D, find the period, then we know that omega is equal to 2 pi on the period, or the period is equal to 2 pi on omega, which means we'd be looking at 2 pi on 2, which would be pi seconds. So that means it completes one cycle in pi seconds. Okay, so that should be enough information to complete the lesson, and that's how we use circular motion in an applied sense.